All right, part two. All right, so part two, there's something you're not going to have to do, but it's sort of what happens here with what we're saying. I said that in the last video, I said that we can get fields from using that spherical distribution from Coulomb's law. Basically, we can use that spherical distribution, just say something's made up of a lot of tiny spherical points, each with a charge, and then that adds up to the field from that object, right, from each one of those tiny charges. And it turns out that's really true, right? Because the charges come from the electrons. The electrons are these tiny point particles that are less than 10 to the minus 22 meters, and as far as we can tell, completely symmetric. We don't know that they're completely symmetric, but people keep trying to figure out how symmetric the charge or the field coming out of the charges is, out of those elementary charges, which are electrons, is, and they seem to be completely spherically symmetric. So it looks like we have these infinitely small, or at least much, much smaller than 10 to the minus 22 meters, about 100,000 times smaller than the radius of a nucleus of an atom, I think. We have these absolutely tiny things that are smaller than we can measure, and they're spherically symmetric, and that's where all the charge is coming from. So the calculations that we do look very much like what we actually think the world looks like. Only then we throw calculus in there, and we don't think the world looks like calculus at all. So we have fields from non-spherical charge distributions. Can be produced from sums of infinitesimally tiny spheres. For example, what you could do is if you had a wire like that, and you wanted to figure out what the field was coming out of the wire, this is approximately the same field as if you took a bunch of spheres, packed them into that wire thing there, so that each one of these spheres had the right amount of charge to end up with the same density of charge there. My notes got wet, which means I have to rewrite them before I scan them for you. So I'm sorry about that. It's actually what's in my head after that happens. Okay, so then we end up with a couple of different ways to do this. So a charge like this from a wire ends up having this radially outward direction, so it's, if I do that in cross section, the field comes out like this from the line charge distribution. So that field is going to be that Coulomb constant times lambda over r. I have to draw the Greek letters backwards as well. Okay, so that's the linear charge density divided by the distance from the center. And then if we had a plate, the field comes directly out of the plate. Okay, and there, for a we'll call that a flat surface charge density. Sigma. Then the field is equal to 1/2 KE times sigma. In that case, it turns out that this is a uniform field. That's how you get a uniform field, is from a flat plate. When we talk about capacitors, when we talk about the parallel plate capacitor, this is the reason why we end up doing it a lot, is because the fields inside are nice and easy. Okay, and that's what we like, is the easy stuff, right? That's what we're going for. All right, so that's more or less what I've got there. I'll do in the example a surface charge density, find the field from that. Then in the next example, in the example for point 3, I'll include something from the line charge, the linear charge density, as part of that example. All right?